Hi, Christian Wallace from Christian Wallace and Associates, and I'm presenting to you, NASA, about space tiles of the future. Our task was to improve the exterior engineering tiles on the space shuttles while economically retaining in the budget given. We were given $15 million by NASA to cost-effectively produce engineering tiles for the space shuttles. While engineering these tiles, we had to stay within the constraints of the atmosphere, and we had to deal with the constant factors of gas and heat and cold temperatures in space. So just a little fun fact about the atmosphere. It's about 300 miles thick, and it weighs 5.5 times 10 to the 18th kilograms. So that's very heavy. And 1 kilogram is equal to about 2.2 pounds. And when you're flying in an airplane around the atmosphere, you can notice the atmosphere around 120 kilometers in the air. So next we focus on our client's needs. We realized that the physical properties you guys needed for the material is very difficult. It needed a high specific heat, high hardness, high melting point, while having a low mass, low density, and low elasticity. We needed a low elasticity and density and mass because while those are important, they needed to be low in order for the tiles not to interrupt the space shuttle. So just to define a couple of those things, a high melting point is how long the material can withstand heat until it melts. A high specific heat is how long or how much energy the material can withstand before the temperature changes. Elasticity is how far it could stretch before breaking, and hardness is if it can withstand extreme pressure. So we had a few groups to choose from. We had ceramics, woods, polymers, and metals. And woods weren't hard enough and didn't have a good specific heat and melting point. Metals, they had a good hardness and good tensile strength, but it was just not the right group for us. Polymers had too high elasticity and too low of density, so we landed on ceramics because they had good hardness and good tensile strength. So, after realizing the intensity of entry and re-entry of the atmosphere and how you had to go through 300 miles of thick, hot, very gaseous atmosphere, we landed on silicon carbide, a ceramic, as our top choice for the material. And so we had to factor in the chemical properties of oxygen, nitrogen, argon to make sure that the silicon carbide wouldn't break when going through the atmosphere. Since while you're re-entering and entering the atmosphere, it could get up to 1600 Celsius, which is about 3,000 degrees. That's very hot. Another fun fact about silicon carbide, it's harder than diamond, which is very hard. Diamond is probably one of the hardest substances on Earth, and so silicon carbide was perfect for us. So on an intramolecular level, silicon carbide is silicon and carbide put together. Both are nonmetals. And nonmetals make covalent bonds, which are the strongest of all the bonds. So this is our proposed plan. We propose to place around 100 to 200 tiles around the nose and the tip of the space shuttle. And yeah, the ratio of silicon to carbide is 1:1 because it is a crystal, so it forever expands. The good part about silicon carbide is that it's covalent bond, as I said before. It is very strong, the strongest of all of them. And the covalent bond is when you have a silicon or a nonmetal and a carbon and a nonmetal. And they're attached between two electrons right here, and they share the two electrons. And this line right here is the strongest bond between two elements. So, in conclusion, Christian Wallace and Associates, we plan on changing the future for NASA and space travel in general. Silicon carbide is the best material we could find for you guys. It is strong and the best. Thank you, NASA, for listening to our proposal.